Welcome back. Statics is probably one of the more important engineering disciplines that you'll study, and in fact it's usually your very first actual engineering course once you get beyond the basic physics from this, because there are many instances where you want to build something that won't fall down, something that you don't want to move, as the case may be. So statics is the art of designing a structure that won't move, and that comes down to the idea of having it in equilibrium. Equilibrium means all of the forces are balanced out. In other words, the net force equals zero. Think about what you know about Newton's second law. If the net force is zero, what does the acceleration have to be? Well, that's going to be zero as well. And it's also going to mean, of course, that there's no change in momentum. In other words, the object is going to stand perfectly still. So we're going to take a look at a typical statics case. We're going to have you build a sign for your great robotics engineering shop that you're going to put up once you get out and into the real world. Let's get started. Alright, so let's take a look at our situation here. So you're going to have a wall for your shop, and these little hash marks just in engineering just mean it's a solid wall. And then coming out from here is a rod, and attached to the rod then is a little short cable and our sign. And then to help hold the sign up, we have a cable going out like this that attaches itself to the end. So what I want you to do is pause the video and identify all of the forces that might be acting on this. Just go ahead and sketch them in your book and let's see how well you can do. So if you pause the video, because this is a really important exercise, this is really the first step in any kind of statics problem that you're going to do, is you're going to have to figure out what forces are acting on it. Alright, well, probably the most obvious one then is going to be the force of gravity of the sign, the weight of sign. What you may not have thought about is that this rod also has weight. So we would have the force of gravity on the rod. If you think about it, that's pulling down. That's something else that that cable has to hold up. And then the cable itself is providing a tension in this way, and it is a vector because it's going to be in two dimensions. Now, F of G, the force of gravity on the rod, the force of gravity on the sign, those are also vectors, but they're only in one dimension. So let's go ahead and draw our coordinate system here. So we'll put it like this. And so we'll call this our positive j hat direction, and we'll call this our positive I hat direction, just like we've done before. So given that then, what can you say about the signs of these, the directions? Well, they must be negative. I need them to be vectors. So this now is a vector. It's a scalar magnitude. So my f of gr is a scalar magnitude plus the direction, the negative sign. So that makes it into a vector. Now t is not so easy because it's got both an I hat and a j hat component. Now there's one other force that you might mention. What might that be? Well, there's also a tension in the sign cable. We'll call that TS. Now, what direction is that acting? That must be acting in the positive j hat direction. It's going this way. But it turns out that that force, that tension, actually doesn't matter much because we'll show you why. We want this to be in equilibrium, so we want the sum of all the forces. Let's look at just this object right here, just our sign. So the forces on the sign then would have to be positive tension in the sign and then minus f of g of the sign. Well, but that's got to equal zero because they're going to be in equilibrium. We don't want any forces there. So all that says is, we've got a g there, we mean that to be an s. All that says is that the tension in the cable is simply equal to the weight of the sign from that. Okay, so I could instead, so I'm going to be looking at the forces on the rod. Well, the force on the rod is this TS, this T, and the rod itself. But we do know that the sign is producing that tension because they're actually equal to each other. So this is a shortcut that you're often going to take if and only if you recognize that it's in equilibrium and that is all the forces that happen to be acting on it. In some cases, I might have more forces than that. But either way, you should be able to see that if I'm adding up all the forces on here, I'm going to have T of S, my tension cable for my sign cable, my weight of the rod, and my tension in the rope, but that tension in the sign cable is going to be equal to the weight, equal in magnitude to the weight of the sign itself. Okay. All right. So that might be basically all that we've got to worry about right now. We'll see a little bit later. There might be a little bit more to that. So turn over to the next page then. And here we're given all of our components here. So for example, we are told that the mass of the sine is, let's put this in step 3 since we've got the space for it. So the mass of our sine is 5.5 kilograms. And the mass of the rod is 2.0 kilograms. So the rod is supported by this cable, and the cable is mounted at 35 degrees. Let's repeat our sketch over here. You can have your 2 pages available so that you don't have to keep bouncing back and forth. So I've got my wall and my rod and my sine, and here's my cable. And so it's 35 degrees from the horizontal. That means this. So this angle right here is 35 degrees. Okay. So we'll go ahead and call that theta of the cable is going to equal 35 degrees. Okay. So we're ignoring the mass of the cable because that's obviously going to be much smaller than the mass of the rod or the sine, either one. So we're ignoring it only in the sense that the mass of the rod, for example, is much greater than the mass of the cable. And so therefore it's not going to have any effect on what we're doing, not any effect that we can detect anyway. Okay. Now what we want to know is, what is the tension in the cable? And we don't know what that is offhand, right? And that's going to be in newtons. Okay. Now some other things that we're going to need is we're going to need all the other forces should be gone. We should go ahead and list them here. So we've got the force of gravity on the sine, and that's a vector. And then we've got the force of gravity on the rod, and that's a vector. We can go ahead now, we know that that's the weight. So you are at a stage in your career where you should be able to go straight to what that is, and that's just m times g. So pull out your calculators, and let's do this together. Find mine. All right, so pull out your calculators. So we're going to quickly just find this weight, because you're going to get to where you can just do this quickly. So it's going to be 5.5 for the sine. It's 5.5 kilograms times 9.81. So it has a weight of 53 point, well, it's really about 54.0. So let's go ahead and use that, 54.0. Now, this is a vector. So this weight is in a specific direction. So here's the weight of my sine here. And remember, we decided that this was going to be the j-hat direction, and we decided that this was going to be the i-hat direction. So what is the vector for that? Well, how much of that force is in the i-hat direction? None of it, right? It's going to be 0 newtons in the i-hat direction. And then how much is going to be in the j-hat direction? Well, that's where our weight is. And so that's what we figured out was going to be 54. We'll go ahead and leave our 0.0 newtons in the j-hat. However, is it in the positive or the negative j-hat? It's in the negative j-hat. That's going to be very important. This is still a vector. It's got a direction. It's got to have a sign. So these two components added together gives me my total vector. Remember, our first step when we're working 2 dimensions is put every single force into components. Well, let's do the same thing with our rod here. So our rod is hanging down this way. This is the force of gravity on our rod. This is the force of gravity on our sine. And we'll go ahead, for completeness, we'll go ahead and say that that's t. And then we said this was minus and this was minus. Okay, so let's find that vector rod. So we know that the mass is 2.0, so 2 times 9.81, and we're getting 19.6. With this one, is there any force, is the force of gravity on the rod, is there any of that force in the i-hat direction? No. So that one's also 0 newtons in the i-hat direction, plus, and this time it's going to be 19.6 newtons in the j-hat direction, but is it positive or is it negative? It's going to be negative. So there's my 2 weight vectors. So there's 2 of my vectors already worked out. I now need to break this last vector, the tension, into components, but I don't know the value of the tension. That's what I'm looking for. So all we need to do then, let me make my triangle nice and big here so that we can see what we're doing. We know that this is theta, and we know that this is the t-j-hat component, and we know that this is the t-i-hat component, and this is just t right here. So how would I get the i-hat component? What would the I component be? So that's the adjacent side. So we have cosine of theta is going to equal the adjacent over the hypotenuse, so ti over t. And then we solve that for ti, and so ti equals t cosine theta. And you're going to get used to this construction very quickly. It's going to be the magnitude times either cosine or sine. Don't assume that the horizontal is always cosine, because it won't be. But either cosine or sine of the angle there. Now, to find the j-hat direction, that's the opposite over the hypotenuse, and so that's going to be the sine. So the sine of theta is going to equal t in the j-hat divided by t, which tells me that t in the j-hat direction must be t sine theta. And a quick tip, as we've said before, if you found which component is cosine, the other one's going to be sine. If you find that this component is sine, well, then the other one's going to be cosine. All right, so now we have our components. So we know that t then is going to equal ti in the I hat plus tj in the j hat. Now what about directions? It's going to be in the positive j hat direction, right? But it's going to be in the negative I hat direction. Make that so that's a little bit more clear. And then we also have our equations for getting those. Now here's your choice. These are not numbers, you can't calculate them. So you can make a very strong argument that they need to be in the equation section, and that's perfectly fine. Alternatively, you can list them in here. You could say something like ti is equal to t cosine theta and tj is equal to t sine theta, but that's up to you. A lot of people are going to want to just keep these organized by having all my equations somewhere else. And so I'm going to save my step 3, my symbols, for only things that I can actually calculate or that I want at the end. Okay, so looking at our design then, now that we've got everything identified here, we've already done this. Our first step is always break all vectors, not just forces, but all vectors into components. We always do that. Okay. Now we need to do that right there means equilibrium. Sum of the forces is 0. That means they're in equilibrium. There's no acceleration acting on that. So we need that in the I hat direction. And if it's going to be in equilibrium totally, we are going to need that to be in the j hat direction as well. And they have to be independent. So just because I'm in equilibrium in the I hat direction does not mean that I'm going to be in equilibrium in the j hat direction. And then our final step, which I'll just put down here, is combine our components back into magnitude direction, because we need to know what the magnitude of that tension is. So there's our plan. That's what we've got worked out. We've got all of our symbols identified, and we should be good to go, right? All right. So let's take a look then on the next page. So we're going to write all of our equations that we have. Well, we've basically got our equations in step 2, remember? We said that we want for the I hat component, we want the sum of our forces, and we'll remind ourselves that that's in the I hat, must equal 0. And that equals, of course, looking back to your picture in the I hat direction, the only force that I have in the I hat direction is Ti. And it's in the negative I hat direction. Let me make that a little more clear that that's an I. And that's in the negative I hat direction. So that one's done, right? Now in the j direction, then we need the same thing. Some of our forces in the j direction must equal 0, so let's write down all of those. Well, we've got going in the positive j direction, the only one that we have is going to be tj. And then I've got minus f of g rod minus f of g sine. So there we go. So how many equations do we have? Well, we've got 2. So one for each one of the equilibrium statements, Newton's second law equals 0, for each of our components. And how many unknowns do we have? Well, we've got 2. We need our Ti and our Tj. That's our 2 components. So we've got 2 equations, 2 unknowns. We're good, right? Everything looks good. All right, take a look at this next little wrinkle here though. If we look at our horizontal component that we have up here, then we got something that looked like, I'm just going to copy it down here, is minus ti. We call it tx here, but it's up to you. Generally speaking, we're going to use an I because x doesn't necessarily mean horizontal, it just means your position. Okay, well, what this says then, this is the same thing as saying that the tension in the I-hat direction is 0. But that's crazy, right? You know that it is actually pulling in that direction because it's a vector. If it was going just strictly in the j-hat direction, then it would only be pulling straight up. And yes, I could hang my sign that way. That would be fine. That would be like, one of these spinny signs or something. But looking at the diagram, we know that there is an I-hat component. So something's wrong. And so here we're going to introduce the next piece, which is critical in basically every statics problem that you're going to do. So we're going to introduce this concept of the normal force. And we've mentioned it briefly before, but a normal force is the force of that wall pushing back. Let me draw our wall here. And here's our rod, right? And here's our tension. And just for completeness, we'll draw the sign in here. So I have a tension acting this way. And that is the same as saying I have a tension acting this way and a tension acting this way. Now, we can probably understand that Tj needs to be balanced out by our f of gr and our f of g sine. That's what this equation right here is saying, is that all those have to equal to 0. However, if this wall were not pushing back against that cable, then the cable would just push that rod right through that brick wall there. And since that's not happening, there must be another force. That force is the normal force. And that normal force is the force of the wall pushing back. Now, normal does not mean not weird. As we've talked about, normal means perpendicular. And what's really causing this normal force is really the repulsion of the atoms. I mean, your hand is mostly empty space. And if you try to push through a table, though, you're not going to be able to. Even that table is also empty space. However, the outer shell electrons in the atoms and molecules in your hand are all going to repel those outer shell here. Now, overall, it's neutral, but your electrons are going to have that closer negative repulsion, and that's why you simply can't push it in. We could also go all the way down to the nucleus and talk about strong forces and things like that. We're just going to keep it a little bit simple. So the idea, though, is the stronger you push on this, the more that wall is going to push back. And if you think about it, if you've got two magnets, and these are not magnets, by the way, but just use this as a demo. If I have two magnets, the closer they are together, the harder those magnets are going to push against each other. So that's what's happening with this normal force. So the normal force, if you look on the next page, the normal force has two characteristics. First of all, it's normal. It's always perpendicular to whatever surface. In this case, if this is my wall, my normal force has to be perpendicular to it. I cannot apply a normal force at an angle. It never happens. It will not be normal at that point. And that's going to be a really important thing later on. So remember, the normal force has to be perpendicular to the surface. And then it's equal and opposite to whatever forces are applied. So in this case, we're applying this force Ti. That's the I component of our tension. Well, these two then are the ones that have to be equal. All right, so that's going to mean then that I'm going to need to include that normal force in my final answer here. So we kind of seem like we have a problem now, right? Let's go ahead and redraw our picture so that we've got it here where we can work with. So here's my rod, and my sign, and my cable. And now we know that, writing our components, I have Ti in this direction, I have Tj in this direction. That looks like an F, so let's make that an I, or a T. There we go. And then, of course, I have my total tension in this direction. I have my F of G sine here, I have my F of G rod here, but then I also have a normal force being applied by the wall. So go back and revise your step 4 equations so that you're including the normal force. Let's do that right quick. Pause the video, make it happen. All right, so you should have gotten for the I hat component, we now have the sum of the forces in the I hat direction must equal 0, which must equal now the tension is, redraw our coordinate system here. Oops, that's going to be I hat. And this is going to be my J hat here. All right, so the normal force is going to be in the positive I hat direction. So this is now a scalar magnitude. And then my tension, I component of my tension is going to be in that direction. Okay, so let's copy down this one just so that we can see it. This one didn't, the second direction, the J hat direction didn't change, but we were going to have our positive Tj minus f of gr minus f of g sine, and that equals 0. So on the surface, it looks like we've got a problem here. We've got 3 unknowns, Ti, Tj, f of n, but we have only 2 equations. So that might be an issue, except for the fact that trigonometry is going to come to our rescue. So remember that we only need t, which means I could actually get it, if I could get this from, then I can get t because I know I can get my total t without having to work with the horizontal component at all. Let's see if that makes sense. So I know, let's draw our triangle here. I know this angle right there. And if I knew what this Tj was, could I get t? Sure, right? That's going to be the sine. So this would be sine of theta is equal to the opposite, which is Tj, over t. But this time I would be solving for t instead of solving for Tj. So let's just do that, even though we're going to do it later on. My t comes over here, and then I'm going to divide over here. So I divide both sides by sine theta and multiply both sides by t, and this is what I get. So here is my third equation then. And so if I can get my Tj, I can get that t, and I already know the direction, which means I don't actually even need this. The reason is that I really now only have 2 unknowns, but my unknowns are Tj and t. And so I only need this equation and this equation. So these are the kind of clever things that you're going to need to think about when we start looking at things in multiple dimensions, in 2 dimensions in this case. So you may say, well, why would I bother with this? Well, we're going to talk about what we do with that in just a minute. But for now, just to get the tension, which is all it asks for, I actually don't need the horizontal component. I only need to use the vertical component. Well, that's going to speed things up tremendously. All right, so down here in the bottom of step 5 then, let's go ahead and let's work out our final answer. Why don't you pause the video and see if you can get it? And then let's compare to what I get. So pause the video and do that now. Did you pause the video? It's really important that you do these kind of practice things so that you're ready for the exam, you feel confident doing the homework, things like that. All right, so we're only going to deal with the J hat component. So I know that the sum of my forces in the J direction is going to equal 0 because they're in equilibrium. That statement right there, that sum of forces equals 0, means it's in equilibrium. And then I'm going to have that is plus Tj minus f of gr minus f of gs. Well, I know f of gr and I know f of gs, so I just wrote those down in my symbol list. So we're going to solve this for Tj. All right, well, that's going to be pretty easy. I'm going to move my 2 forces to the other side, my 2 gravity forces to the other side, since they're negative, and that'll make them positive, and that equals Tj. Simple as that. We can add these because both of these are strictly in the J hat direction. Remember, I have to treat these as 2 separate problems. I can only work with the J hat stuff together, and I can only work with the I hat stuff together. I can't start mixing them up right away. All right, so let's go back to our symbol list, and we can get our masses. I don't have that handy, so we're going to work it out again right quick. So it was 5.5 kilograms times 9.81. So F of GS then we decided was 54.0 newtons. And then we had 2 kilograms times 9.81. And so this was, F of GR was 19.6 newtons. Both of these are in the J hat direction, and that equals TJ. So we just add them up. So plus 54, and I'm getting that TJ is equal to 73.6 newtons. I'm not done though, because what I actually want is T. Well, okay, I have now used this equation, so now all I need to do is use my other equation. All right, so let's do that now. So I know that T is going to equal TJ over sine theta, and that's going to equal 73.6 newtons divided by the sine of whatever our angle was, which I believe was 25 degrees, but maybe we better look that up before we get too far. 35 degrees. Okay, so 35 degrees. Just make sure that we're making it match. I've got a disadvantage. I can only see one page at a time. You get to see the whole thing. Okay, so we're going to do 73.6, and we're going to divide that by sine of 35. And T then, the total tension, the magnitude of the total tension is 128 newtons. That is not the tension vector. That is just the magnitude, and it asks for the tension vector. But that's easy, right? Because T as a vector is equal to 128 newtons at 35 degrees from horizontal. And that's my final vector. And that is really all there is to it. So these problems can be deceptively simple. Now, one thing you notice, this equation was not in our original equation list. But if it comes to you later, you go, oh wait, I can get my tension using this, that's fine. Go back and add it to your step 4. That way you'll have it when you come through and you start trying to review for an exam or something. You'll know, oh, where did that come from? Oh, right. As I was working the problem, I realized, hey, I'm going to need some other way to get this T than what I was working on before. All right, now let's talk about this I hat component equation. So far, we were able to get the tension without using it. We didn't have a problem with that. So let's look at what we've got here. So we're going to design for safety. Let me put my wall back up here. And here's my rod and my cable and my sign. And then there's my support cable there. So when we're looking at the horizontal direction, so what is causing the rod to push into the wall? What's causing the rod to go this way? Well, that's going to be Ti, right? The tension, the horizontal component of the tension force is pushing that rod into the wall. Well, the wall then, the force exerted by the rod on the wall then is simply going to be Ti. And we know that that must be equal to the normal force. Let's remind ourselves why that's true. This is in the I hat direction. This is in equilibrium because it's not crashing through the wall. So that means that adding up my forces, let's remind ourselves of our coordinate system. This is I hat, this is J hat. Can't change it once we've set it. And so this means I'm going to have minus Ti plus F of n, because my wall is providing my normal force in that direction. Okay, so these two things, writing this down then, this is minus Ti plus Fn equals 0. So my normal force then is equal to Ti. All right, can I figure out what that Ti is? Well, sure, because I know the total tension, don't I? So we know that the total tension was going to be the magnitude of the tension. Let's do it over here. The magnitude of the tension was 128 newtons, and then our direction was going to be at 35 degrees from the horizontal. Let's draw our triangle. Draw these triangles. It's going to help you. So I've got something that looks like this. This was my total T. That was my magnitude. This is Ti. This is Tj. And this angle is 35 degrees. So if I want to get Ti, how would I do that? Well, I'm just going to take the cosine here since I already have my t vector. So cosine is the adjacent, so cosine 35 degrees is going to equal my adjacent, which is 2ti, divided by my hypotenuse, which is t. So t cosine 35 is going to equal ti. Let's put that in your calculator and let's find out. So t is 128 newtons times the cosine of 35 degrees. So 128 times 35 cosine. And we get that Ti is equal to 105 newtons. Now just a side note here, notice that we used something we calculated to get that answer because it was here, it was obvious. However, if there's a mistake in this, there's going to be a mistake in this as well. So one approach you could take is to not use this thing that we calculated. Instead, we know Tj, but we also calculated that one, didn't we? So I don't know that we're gaining a whole lot, but let's suppose that you feel more confident about that one. Well, then if I want to find Ti, what trig function do I want to use? In that case, I'm going to use the tangent. So I would use tangent 35 is going to be 35 degrees. Let's make that a little more obvious that it's an n. So tangent 35 degrees is going to equal my opposite over my adjacent, so that's going to be Tj over Ti. I wanted Tj, so that gives me Ti is equal to, I'm sorry, I wanted Ti, so that's Tj divided by tangent 35. And that's going to give you exactly the same answer. So be aware that there's usually multiple ways. You've got 3 sides on the triangle and you only need 2 at a time. So you decide which one's going to be easiest, but always keep that in the back of your mind that, wait a minute, if I need this, maybe I can use a different trig function and get what it is that I'm looking for. All right, so how much normal force must the wall provide then? Well, it's right here. It has to be equal because we want it to be in our equilibrium state. So it has to, it's already, we've got it worked out, so it's in equilibrium in the vertical part. We need it in the horizontal, in the i-hat direction as well. So that tells me that my normal force then must be equal to positive 105 newtons in the i-hat direction. Ti, remember, was in the negative i-hat direction, but their magnitudes definitely have to be the same. And then I come back and I go ahead and when I want to make it into a vector, these of course are magnitudes because I took care of their direction here. So these are scalar magnitudes, always the best way to do it. And now these 2 magnitudes have to be the same. And if I want the normal force vector, then I just simply look at my picture and I go, oh, that's going to be the positive direction, and we're good. So when we're thinking about designing for safety then, suppose the wall can provide up to 4,000 newtons of force before it collapses, because you're going to need some sort of a wrecking ball to push through this. Is your sign safe? Well, sure, because the wall is only having to do 105 newtons, so we're easily fine. We're not going to have any problem whatsoever. So our wall is completely safe. Okay. Now, just as an aside, there is a limit to what it can provide, and in this case we said that that's that 4,000 newtons. So if you want to tear the wall down, the only way you're going to be able to do that is to apply a force to that wall that exceeds 4,000 newtons. So the I component of that wall, of that force that you're applying, must exceed our 4,000 newtons. So see, go back through this and make sure that it makes sense to you. Make sure that you can follow everything that we're doing here. We're just using equilibrium, and remember that equilibrium is nothing more than the statement of Newton's second law that the acceleration is 0. Okay? All right. If you have any questions about this, make sure that you come online, meet me in person, or make a discussion post, and I'll be glad to help you there. So now we've gotten just a basic introduction to statics and with the idea of equilibrium and the normal force. Remember that statics, by definition, means that the object is in equilibrium. Static means it's not moving. And the only way that's possible is if the sum of my forces is equal to 0. So when you're trying to design an object or design some sort of a structure, you really want to think about, okay, how am I going to do this so that all of my forces are 0? Eventually, not only are we going to try to get our lateral forces to be 0, but we're also going to want our rotational forces to be 0. And we'll talk about how that works when we get into our rotational section. But it's almost exactly the same as what we're doing here. So if you understand what's going on with equilibrium, then you're going to be fine when it comes to statics. When we're talking about the normal force, we're going to use that in a lot of other ways. For example, the frictional force depends upon the normal force. So keep that in the back of your mind as we start moving to talk about friction and some of the other applications of the normal force. We'll see you next time.